So thanks a lot, Peter, for the introduction. I'd like to start by saying it's a big honor to be here, and I'm, revealing too much, too soon. It's a big honor to be here, and I'm very grateful to Professor Agnate for the invitation. It's an honor to be here to talk after Bob, so I was quite nervous before. But anyway, so I will be sharing with you some recent work on phase field modeling of fracture. It's not too hard to introduce the topic because Tom already did the job, and also this morning there was the talk by Professor Holzapfel. Nevertheless, I will still very, very briefly go through an introduction. So once upon a time, there was Griffith with its well-known energy balance. So the energy release per unit advancement of an existing crack has to be equal to the energy consumption for the creation of a new surface in critical conditions. And this quantity is postulated to be a material parameter, which is the fracture energy. So this is brittle fracture according to Griffith. Many years later, Francfort and Marigot in France, they developed a variational interpretation in a sense. Well, they reformulated the problem, one can say, in a variational sense. And so here you have an energy functional, which contains the displacement field and the unknown crack, an unknown measure of the crack in a sense, where you have then an integral over the volume of the elastic strain energy density plus a surface integral over an unknown surface, which is the surface of the crack multiplied by the fracture energy. And so the minimization of this energy functional is was shown by Francfort and Marigot to be, in a sense, equivalent to Griffith's problem. But a major step forward, I mean, this problem is now very difficult to treat because gamma is itself an unknown. So from a numerical standpoint, it's an intractable problem. So a major step forward came in year 2000 when Bourdain and Francfort and Marigot introduced a regularization. Interestingly, this problem was very similar to a problem being tackled in image processing by Mumford and Cha. And an analogous regularization was then carried out using the so-called Ambrosio and Tortorelli regularization functional, which shows up here. So basically now we have another energy functional where instead of having the crack set as unknown, we have a continuous field, which is called the crack phase field, which is termed here D. This field takes values between 0 and 1, whereas 0 is now the intact material and 1 is the completely broken material. And you see here you have, first of all, a coupling function in the which multiplies the elastic strain energy density in the first integral, but perhaps more strikingly, the second integral is no longer a surface integral, but a volume integral over the entire volume. And this is what Professor Mie called the crack energy density. So it's now, this is the Ambrosio and Tortorelli functional. It contains the phase field and the gradient of the phase field. And since this is now a volume integral, no longer a surface integral, we also have a length scale coming into the picture. And this length scale L plays an important role. I will show you more about this in the future slides. Now, very importantly, it was mathematically proven that the solution of this problem has an important feature, and so the and namely, if L tends to 0, then we get gamma convergence. So let's say the minimizers and minima, the global minima and isolated local minima of this problem, they gamma converge to those of the Griffith problem. So this is a property that was very crucial for some of the developments in this area. But this is now not the final recipe yet, because one needs to ensure that cracking occurs under tension and not under compression. So a very important ingredient was introduced shortly later, and it consists of a split of the elastic strain energy density in the first integral in two components, a positive component and a negative component. This was proposed by Amor and Marigot and Maurini in 2009, and also by Professor Mie in 2010. They performed a split in different ways. I will again come back to this aspect later. And finally, there is another missing ingredient in a sense. If you interpret the phase field now as a sort of damage parameter, then you also want to ensure that damage is not reversible. So you also want an irreversibility condition, that the phase field can only increase. And finally, Tom already talked about a higher order formulation, so I don't need to spend any more time on this. So, just to give you a graphical interpretation of what the phase field can look like in a problem, if you have here a propagating crack and you want to describe this with phase field modeling, you're basically replacing the discrete crack with a steep variation of the continuous phase field. And as you see, almost everywhere you have d equal to 0, but very close to the crack you will have a very steep variation of d, and the support of the phase field will have a characteristic width, in a sense, which is proportional to L, to the length scale. So it's quite intuitive to understand. As L tends to 0, then you recover a discrete crack. But of course, you cannot afford this from a numerical standpoint, because in a numerical method, you need to resolve this steep variation with a sufficiently fine mesh. So if you look at the phase field method in the global context of computational methods for fracture, of course this is just a partial view. There are many more methods, but so what are the advantages? The most striking advantage in my view is the great flexibility. You don't need any ad hoc criteria. Once you have your energy functional, you can basically deal with initiation, propagation, merging, branching of cracks. So with any arbitrarily complex topology of cracking, by just minimizing the functional, which means effectively by just solving PDEs. And so you can do this on a fixed mesh and in 3D without big trouble. But the disadvantages are, of course, that you need a fine mesh because you need to resolve the steep variation. So the smaller L, the finer your mesh needs to be. And as I'll tell you in a second, there are still some issues in the efficiency and robustness of the solutions procedures. So in my group in the past 3-4 years, we've been working quite intensively in this area, and we've been tackling different aspects. One of them is ductile fracture, but I gave a talk 2 years ago at Complas on ductile fracture, so I won't address this topic today. We started working about fatigue, but this is very preliminary still. We are working currently at the coupling between fracture and transport, and I will briefly touch upon this today. We are at the same time also looking at solution schemes and multi-scale modeling approaches, and also we've been tackling recently fracture in shells. Of course, don't worry, I won't have time to talk about all this. This is an outline of what I would like to share with you today. I'd like to share some good news, but also some, I wouldn't say bad news, but some not so good news, because I think it's fair not to slip anything under the carpet and to also tell the problematic side of the story. And also this can be maybe of encouragement to some of you to help us solving these problems. So some recent good news are quantitative validation in brittle fracture that I'd like to describe. Then I'll briefly talk about fracture in shells, the critical issue there and how we solved it. And then we'll also show some results on desiccation cracking in porous media. And then, as I said, I will talk about future challenges which are still unsolved, so the issue of efficiency versus robustness, and the issues related to how the split is performed between positive and negative components, and also non-uniqueness of the solution. And finally, I'll draw a few conclusions. So let's start about talking about quantitative validation. There has been a lot of qualitative validation in this field, but not so much quantitative validation. Here I'm talking about brittle fracture. These are experiments done on cement mortar. These experiments were performed at LMT Kashan by Andrea Carpiu-Prisacari for her PhD thesis, supervised by Martin Poncelet. And these are very unique experiments in a way because of different reasons. First of all, they were performed with an hexapod with a multi-axial testing machine that has 6 degrees of freedom, so can apply very complicated loading histories. And secondly, they had a full field displacement measurements through DIC. So in other words, we had the possibility to know exactly the boundary conditions on the surface, external surface of the specimen, at the same time top and bottom, where the specimen was loaded. At the same same time, we could then also compare our computations with the surface fields that were also known on the side surfaces. And thirdly, the experimentators, they were using an integrated input-output DIC algorithm, so they could control loading based on results of the DIC computation. So in a sense, this was an interactive set of tests, so they could achieve very stable crack propagation even after very complicated loading. So I will just show a few results. Now, it's important to say that we didn't fit any parameters in the comparisons. What we did was, first of all, we needed, of course, some material properties for our model, not many, but we needed elastic modulus, and this was characterized with independent tests. We set the Poisson's ratio to 0.2, and then also the tensile strength was characterized by independent tests. And regarding the fracture energy, we were performing, or they were performing, some 3-point bending tests, and these 3-point bending tests were then compared with results of our computations based on phase field modeling again. So through this calibration, we came up with the value of the fracture energy. So the only missing value was the length scale that I was mentioning, but already Tom showed in one of his slides the relationship that exists between critical stress, elastic modulus, fracture energy, and the length scale. This relationship comes from the solution of the homogeneous version of the phase field evolution equation. It's very well known and has been used previously also to calibrate this quantity. So in other words, we could compute the length scale based on this relationship, so we didn't have any free parameters left. So in the comparison, we didn't adjust anything. So I show you some representative results. These are horizontal displacement contours. Here you see those from the DIC on the left-hand side, and here you see those from our computations. You see that the crack starts propagating upwards. Then there is, due to the complicated loading history, the crack deflects and starts going downwards, and this happens in both. And then there is a further deflection upwards, which is also captured by the model. And finally, there is a crack branching phenomenon, which is also captured by the model. So we were very happy about this, but these are still qualitative in a sense. Regarding the crack pattern, at the end, you have two apparently different patterns, but if you look inside the specimen with some sophisticated experimental techniques they were using, you see that the crack branching is indeed there. Only it didn't make it up to the surface, but it was indeed there. And even the angle was in very good agreement with results. But even more importantly, this is the real quantitative comparison. If you look at the normal force and the shear force, which has a very complicated trend due to this intentionally very complex loading history, you see that the match is, to me, quite remarkable. It's a really good match. So we were very satisfied with these results, and we, without need for any fitting. As I said, another topic that we wanted to address was fracture in shells. Of course, there are many motivations for dealing with shells. They are used in many fields of engineering. For efficiency purposes, we addressed fracture in solid shells first, but that was not particularly challenging because solid shells are nothing else but solid elements with some cure for locking. So more challenging was going to Kirchhoff-Love shells, because in that case we only had a midplane. We only have a midplane, and we want to study fracture and account for the fact that the stress, of course, is not constant across the thickness. And this is, as I will show you in a second, this is quite a challenge if you want to have only one phase field on the midplane. You don't want a three-dimensional phase field. So we were using isogeometric Kirchhoff-Love shells because these are very neat to use. They can be rotationless, because if you use p equal 2 at least, then you get for free the continuity requirements. So we were using the isogeometric shells by Kindle. So what is the critical issue in this area? As I was mentioning, the phase field only lives on the mid-surface. And at the same time, you want to account for the fact that the stress field varies over the thickness. Now there had been previous works, in only two. In the first work there had been no positive-negative split, which is in our view unrealistic. And so this was the critical issue that we wanted to tackle, how to perform the split. There had been another proposal. The first proposal to perform the split was the following. Well, as you well know, in shells, most often one proceeds this way. You have an elastic strain energy density per unit volume, and then if you plug in the kinematics of the Kirchhoff shell, then you get the strain energy density per volume as a function of the membrane strain and the curvature tensors, and of course here you have the coordinate over the thickness. And now what you typically do is you integrate in closed form analytically over the thickness, and then you're left with the elastic strain energy density per unit area of the shell, in plane area of the shell, and these are the two components, the membrane, elastic strain energy density, and the curvature part. Now what the first proposal had been was the following. There had been a split of the membrane term into positive and negative parts based on the spectral decomposition of the strain tensor proposed by Professor Cimne. And then basically the degradation function was multiplied by the positive part of the membrane energy and by the entire bending energy. And then the only undegraded portion in the functional was the negative part of the membrane energy. Now, at first glance, it seems like this is a reasonable proposal, but at a closer look, this proposal actually leads, this method actually leads to unrealistic results. And why? Well, first of all, if you happen to have a combination of compressive membrane strains and bending strains, so that the compressive membrane strains are so large that they more than compensate the tensile strains due to the bending effect, then in the end you end up with a fully compressive state of strain. So you would, in this situation, theoretically, you shouldn't have any fracture. And instead, with this approach, you do get fracture, because you're still degrading the entire bending energy. The second reason is that imagine now you have no membrane components at all, you only have a bending situation. In this case, you would degrade the entire bending energy, so this would be like degrading the compressive part as well as the tensile part. So basically this would correspond to the unsplitted case where you're degrading everything. So our approach was the following. We start from the elastic strain energy density per unit volume. We introduce the kinematics, and then we need to perform integration over the thickness, but we perform the split in the positive and negative parts directly on the strain energy density per unit volume. So we introduce here, of course, the kinematics, and then we introduce here the positive-negative split, and then we perform the integration over the thickness in a numerical way. So to do this, we place 3 Gauss points over the thickness and perform numerically the integration. So, and with this, the results were pretty good. We compared KL shell results with solid shell results and also with solid results. And you see this is a simply supported beam where you have a pure bending situation, and results of the proposed formulation are in perfect agreement. Oops, something is wrong here. Are in perfect agreement with results of the solid formulation, and instead, if you were degrading, and these are up here, but if you were degrading the entire bending energy, then you would end up down here, which would correspond effectively to a formulation with no split at all. Again, here you see the case where you have a pre-stressed, simply supported beam, and the pre-stressing is such that you compensate the bending completely. So with this approach, you predict correctly that you have no fracture, so you can go up indefinitely, and instead, with the previous approach, you end up down here. So, and then we were performing some more, let's say, fun examples here. We were checking the capability to merge existing cracks into one crack. This is an annular plate under pressure. So you see we have 4 existing cracks which then propagate and merge, which can be done straightforwardly with the phase field approach. And then we have, in this case, we have nucleation and merging immediately of the crack in 4. And then this is a cylinder where in this case we have a crack that propagates longitudinally, and in this case we have 2 tier straps that are meant to stop the crack and let it deflect. And you see this is exactly what happens. So you can deal with these topological changes in the crack, straightforwardly without need for any special methods. We are in the process of extending this formulation to ductile fracture. As I mentioned, we have been working on ductile fracture some time ago, but we are still in the process of improving the model and extending it. And also we are working at locally refinable B-splines to achieve local refinement, which, as you can imagine, can be very important for efficiency purposes. So then, again, speaking of the good news, the third good new piece of good news I would like to share regards desiccation cracking in partially saturated porous media. So cracking due to loss of saturation in porous media. There was a session devoted to this very topic, which I found very interesting the other day, yesterday, I believe. What is the motivation for this? Well, we know that in soils, for instance, there are extensive phenomena which involve cracking due to desiccation, but also in cementitious materials, for instance, cracking related to shrinkage is highly influenced by these effects. So basically what we did was we combined an approach for Biot theory, so a classical approach for porous media, and especially in the partially saturated conditions, with the phase field approach to fracture. And so I assume Biot's theory is familiar to most of you. I don't have time anyway to review it in detail, but I'll show you the most important equations in the next slide. So in Biot's theory, basically we have 2 unknowns, the displacement field. Actually, I should add that in our let's say version of Biot's theory, we we typically have the solid skeleton, the fluid pressure as in the pores of the solid, but you can also have a gas phase. But in our case, to simplify things, we took the pressure of the air equal to 0, so we eliminated it as unknown. We are working still in isothermal conditions, so we don't have temperature as unknown, and so we are working, let's say, in a more simple version where we have the fluid pressure and the displacement field as unknowns. And then, of course, on top of that, we added the phase field. And we came up then with a model where we have 3 unknown fields. One is the displacement. One is the displacement field. Oh, I have a smaller finger than Bob, but still I have the same problem. 3 unknown fields. One is the displacement field, one is the fluid pressure, and one is the phase field. So in the phase field context, we use the Ambrosio-Tortorelli functional, which is the one I showed you in the very first slide, and we use the tension compression split after Amor, Francfort, and Marigot. So we have basically 3 governing equations: the balance of momentum, which you see here, the mass balance of the liquid water, and the phase field evolution equation. I don't have time, of course, to go into the details. What you see here in these boxes are the quantities that need to be expressed through constitutive laws. One of them is, of course, the stress. You see here we are using the so-called effective stress concept, which is very well known to people working in porous media. This is the saturation. This is the relative velocity between the fluid and the solid. And in this case, you see in the phase field evolution equation, the fracture energy GC is also in a box. A box of different color, but still a box, because it will also be expressed by means of a constitutive law that I'll show you in a second. Oh, okay. So these are the constitutive laws. This is a okay. It's linear elasticity plus phase field, and then we have Darcy's law, and then we have van Genuchten's model, which is a very classical choice for the hydraulic properties. And so the first source of coupling is the use of the effective, is the use of the effective stress, and the second source of coupling could be related to Darcy's law, but in our case we wanted to choose the simplest version possible, not introduce any, let's say, arbitrary components. So we didn't introduce coupling here, but we had a constitutive law which we found from experiments which relates the fracture energy to the water content. So you can recognize here, this is again the homogeneous relationship I showed you before already for calibration. Only here the tensile strength is a function of the water content and the elastic modulus is also a function of the water content. And these functions were known from the literature. So we just plugged them in and we found a fracture energy which is a function of the water content. Then of course we need initial and boundary conditions. We were simulated some experiments by Perron. Oh my God. Where you see, okay, I give up, I'll use this. Where you have a clay cake, which is basically attached to a given base, and then you observe the development of cracks due to the desaturation, and this desaturation is driven by an outward flux, which was known and measured by the experiments. So I'll just show you a little video. This shows from the side what happens in the experiment. From the side, you have a bottom crack, which starts developing, and then, as the time goes by, there is a competition between this bottom crack, which is due to the fact that you have high friction between the lower base of the clay cake and the specimen, and then you start developing cracks due to the loss of saturation in the upper crust of the specimen, where the pressure becomes negative, and so you have desaturated conditions, and then there is a period doubling phenomenon where there are further cracks that form more or less halfway. So now, I have a few minutes left for the bad news, because up to now it seems like everything is great and we can model a lot of different phenomena, which is of course true, but I would like just very briefly to show you what are the open issues, the burning open issues in this business, in a sense. So the functional that I showed you at the beginning, the functional, the energy functional, is convex if you consider it with respect to U only or to D only. But with respect to U and D simultaneously, it's not non-convex. And this is a major source of problems in the solution, because you are looking for minima. You will have several minima, some local minima, and of course a global minimum, but the search for this minima will be much complicated by this non-convexity. So one option, of course, is to go staggered, so to minimize alternatively for one field at a time, and the other option is to go monolithic, but there are bad news. The first approach is robust but inefficient, and the second approach is efficient but not robust. What do I mean? Well, I'll show you in a second very quickly. So one option, of course, is to make the robust scheme efficient using acceleration schemes. The other option is to make the efficient scheme robust. This is something we have tried so far with reasonable success, but certainly there's still a lot of room for improvement. When I say the staggered scheme is not efficient, what I mean is that you need, for instance, in this very time step, 364 iterations of the staggered scheme is if you want to reach a very strict tolerance, of course. And the reason is that the energy tends to decay in a very irregular fashion, because then you can jump from local minimum to local minimum in your search for the global minimum, if you're looking for a global minimum. And okay, we have actually the other issue of robustness is that if you try to go monolithic, your computation will just stop here, because the Newton-Raphson scheme will kiss you goodbye in that way. So we found a way to improve this, and this improvement was related to a spatial line search, which is described in the paper I'm quoting there, but still we could achieve an improvement in the computational speed by 4 times, but certainly there is still a lot of room for improvement. The second issue is the issue of the positive-negative split. Now imagine you have a specimen where you have a full crack that is fully formed. So the specimen is basically made of 2 pieces, and then you displace the upper part horizontally. Now if you use the split by Amor et al., then results are what you expect. So you have rigid body motion, but if you use the split by Mie, you will still have spurious deformations, which means if you use this split in more complex situations, there will be spurious shear stresses just due to this effect. On the other hand, one can say, okay, then let's all use the split by Amor et al. Well, also this split is not perfect. Tiang Li, in a recent PhD thesis at Marigo's group, has shown that if you use the split by Amor et al., you basically are, and if you perform a uniaxial tensile test or a uniaxial compressive test, but on a 3D specimen, so you have lateral strains, you basically end up with a compressive strength that is 1.22 the tensile strength. So that's it. You cannot incorporate any other behavior. So this is also, of course, not optimal. And finally, non-uniqueness. Well, we were performing several tests. I told you already that you have several local minima because the functional is non-convex. So you see here what happens if you slightly perturb the mesh. It's enough to slightly perturb the mesh. Of course, you can slightly perturb material properties of anything else. You end up with different crack patterns based on really minimal changes in, for instance, in this case, in your mesh. So the question is, shall we talk about fracture pattern, one fracture pattern, or shall we rather talk about several fracture patterns, each of them which are given probability to occur? And this is a joint work that is ongoing, I can say, with Herman Mattis and Timothy Gerasimov. Speaking of persons, before I go to the conclusions, I would just like to mention that this, all I have presented was joint work with these guys, Maredi Ambati, Twani Kajui, Timothy Gerasimov, Tao Wu in my group, Josef Kindle, who is now at Trondheim. At that time, he was also in my group in Braunschweig, and Lorenzo Sanavia, who is a colleague at the University of Padova. I forgot to say this at the very beginning, but better late than never. And so, concluding very, very quickly before Professor Rodriguez kicks me out. So we can conclude that phase field modeling of fracture is a very, very powerful tool and a very flexible approach where you can model crack initiation, propagation, merging, branching, a lot of different phenomena in a unified setting on a fixed mesh in 3D. You can achieve quantitative predictions. You can describe extensions also to more complex cases, for instance, ductile fracture, for instance, desiccation cracking, for instance, fatigue. We are still at the beginning of that. And a combination with structural models is also feasible. For instance, I showed you Kirchhoff-Love shells. Results are promising. There is still a lot to do, but the results are very promising. But there are many issues that still remain. The main issues are efficiency and robustness. I'm thinking about algorithms, but I'm also thinking about adaptivity schemes. I'm also thinking about local global approaches to just examine the crack in detail in the regions where this is needed. And there are basic features of the model that still are unclear or are still not satisfactory. One of them is the positive-negative split, but for instance, you may also want that crack faces develop some friction once the crack recloses. In a non-monotonic, for instance, case of loading, you have this issue of non-uniqueness, which needs to be tackled somehow, and there are still many, many more extensions and applications that are waiting to be tackled. Thank you very much for your attention, and happy birthday, Complex.